So I'm gonna like an overview about the geodesy, both in tectonic and volcanic monitoring. So this is the velocity of the last year in Costa Rica based on permanent GPS. So this is the size of Singapore, just in the same scale, just to compare. So we have about 100 GNSS site. So it's one site every 2 kilometers. So this means a lot of data. That's cool, but it's cool, but how to manage all this information, how to get all this information. So because before to start to analyze, you need first that the site is working. If it's not, you have to repair it, you have to download the data, you have to transform the file, process it, generate time series, and so on and so on. So it's quite a lot of resource that you need to do that. And for an observatory, well, especially in OVSICORI, we are not a lot of people to do that. So it's kind of a problem. So it's repetitive first, and you can also delay the diagnostic of the site because if you don't download every day the GPS site, so you cannot see if it's working or not. And well, in total, it's like basically a full-time job for doing all these like kind of a technical operation. And well, when I start like 7 years ago, say, well, we need like speed and we need an automatic system. So we start with an automatic system, which is pretty basic with a database where we record all the GNSS site, and every day of each GNSS site, we have a part of the download for both the local GNSS site and the external, like UNAFCO have some site in Costa Rica and in the neighboring country like Nicaragua and Panama. And we use, after Gamut, Globcat to process, we also create tool to visualize all the data. This is like just like an overview of the database with all the station here and the time here. And each station have one code for each day, which means all these points here around. And with that, you have like kind of an overview of all the processing on all the level of processing of each data for each station. For example, here you can see, well, this is a process with rapid orbit. This is process with final orbit. And you can also see a lot of different code here that is based on the health of the GNSS. It allows us to do a quick diagnostic, to transmit all this information to the technician, and for sometimes to ourselves also, to go on the field and to repair as quickly as possible to minimize the time without data. We know with this system, well, for example, here, we have a red code, so it means like we have a problem with telecommunication. If we have a orange code, it's a problem of receiver. And if we have like yellow code, we have problem with power supply. So this allows us to really to manage our network, our Android station network, and to react quickly. What we have seen with using this system, it's we increment basically each year our annual average working network. So now, well, like in 2019, we were at 93%. In 2020, we were a little bit less because of COVID. It was a little bit harder to maintain all the sites and stuff. But we have seen a clear increase over the year to have such a system and to kind of react quickly. We have also processed 500,000 daily position from 20 to 2021, and this is like the number of daily position through the year as the network was growing and growing. It's good to have a dense GNSS network, but it's way better that it's working. These tools help us a lot to do that. And well, this tool is also an open source, and we have several collaboration with other countries like Colombia and Peru and we share this system based on Python to improve GNSS monitoring in all this country. After, well, it's cool to have time series, but sometimes it's hard to really analyze it. So we have a visualization tool that is web-based. So it's two. There are two panels. With one is just the map with the velocity, and on the right the time series. So you can see the time series here. Each point is 7 day, like a week, weekly solution, and we have also. I lose my mouse. Okay, a Kalman filter that help us to reduce the noise to see better the movement. We can choose time, and dynamically the velocity and its intensity is computed. In red is the horizontal, and in black is vertical. So it's more like a tool, but yeah, it's really necessary to have this kind of tool to really make kind of doing our job more efficiently after. Well, for example, here it's Turrialba volcano. Here, Turrialba volcano and Irasu volcano, as it was in eruption between 2014 and 2018. And there were like 3 million inhabitants downwind of this volcano. And we had this deformation pattern, which was quite interesting because apparently Turrialba go a lot to the northeast, and Irasu was not moving a lot horizontally, but more vertically. So this is the like kind of summary of the eruption. Using this vector, like in red, this is the observation, and in blue, this is the model. We can infer where were the magma and what was the volume. We use both analytic solution and FEM, finite element solution, using the VPVS velocity to constrain here the shear stress, the shear modulus. And we came up with like a reservoir at 8 to 15 kilometers beneath sea level with a volume of 16 to 20 million cubic meter per year accumulated. So another thing that we saw thanks to our Kalman filter is like just before some of the increase of activity, an increase of the vertical velocity. So here in blue, you have like the time series. So it's quite a diluted time series. And with the Kalman filter, we were able to see increment of the velocity. So globally, it's like an uplift, but with some acceleration just before the eruption, though. So it's helped us a lot also to try to forecast an increase of activity. Thanks to this visualization and all this processing that were like always real, like almost real time, we could anticipate 2015, 2016, and 2018 eruptions. We detect two magma area, ponding area below Irasu, which was quite interesting because we will expect that the magma is below Turrialba, but apparently not. So it's like kind of a almost 45-degree conduit, or like, well, we don't know exactly where is the conduit, but yeah, there are like several kilometers in horizontal to reach Turrialba. But we don't know if it's the same reservoir for Irasu, or if the reservoir of Irasu is also offset of several kilometers to the east due to the tectonic setting there. So what people involved in the risk mitigation can ask is, well, what information can provide to have the volume of the magma, intruded magma, and where is the reservoir? So we can link actually the source model with the deformation, with the potential volcanic explosive index. So we do like backdraw. So now we have the reservoir and the volume and the position of the reservoir. So we can infer, well, we have a deformation of 2 to 3 centimeters per year. So 2 to 3 centimeters. So we will expect a volcanic explosivity index between 2 and 3, which what we see basically. And but if we have 12 to 40 centimeters of deformation, then we can expect volcanic explosivity index of 4. So it was quite interesting because at the end, well, we discovered that after after the end of the eruption, but still we can use the same model for next eruptions, or apply this model in other volcanoes, because it's always the question is like, okay, we see deformation, we see seismicity, but what can we expect on term of volcanic explosivity? With that, we can dismiss that we will have a massive eruption with such a small deformation. Back to tectonic. So with this SOGEOD system, we are able to detect, well, slow slip event, the famous slow slip event, but also like kind of the not really slow slip event, what I call loose coupling event, which means like it's like kind of a slow slip, but not really. You will see. And we detect, for example, in 2019, well, we have here a deformation it's a little bit different than the secular one, which is here. Here, normally you have like compression, and after like this lever starting, you know a lot about that. But in 2019, we start to observe difference in the pattern of the formation, and also the incertitude increased, the ellipse of error increased, and like more toward the north west. If we look at that, well, we cannot really infer it, but thanks to this system, we saw like here in the time series that there is a small, really small one here. It's 5 millimeter, so a really small signal here. And if I zoom here, obviously the error are quite big, because it's only few points. Each point is a weak solution, but still it's significant because it's at the opposite of the normal secular movement. And with that, we could infer a model. Well, we can model the deformation even if the uncertainty were big. And we detect here a patch of slip of 4 centimeters. So you can see that it's a little bit different from Sumatra. So it's 4 centimeter here, just really shallow, just at the trench, basically. And this kind of slow slip event, or LCE, loose coupling event, were a magnitude of 6. So it's still consequent, but yeah. A recent paper were analyzing the network and say, well, it's probably it would be really hard to detect it. This is the Xian hole the last year in GGR that say, well, with the uncertainty, it will be really hard to detect. But yeah, we success to detect it. But yeah, uncertainty are big. We have more usual slow slip event. One, we detect a large slow slip event, magnitude 6.8 in the entrance of Nicoya Gulf, which was like way bigger, with deformation up to 1 centimeter. We see like a clear pattern of this this slow slip event here, and with the fact that Nicoya Peninsula is above this seismogenic, or like above the interface, we have also this this pattern of divergent vectors. So here we have a slow slip at depth between 30 and 50 kilometers, with a maximum of a little bit more than 10 centimeter slip at the interface, and it's quite well constrained because we have stations all around this patch. We start to monitor the south of Costa Rica with this sub-horizontal subduction, and with the particularity that it's between three plates, or like, well, the Caribbean or Panama block, the Coco plate, and here the Nazca plate, with between the Coco and the Nazca like a strike slip hold year round. So here we have, I'm just going to focus on 2 events, which was quite interesting. It's some slow slip event, once again, which is the time series of the this site here on the extreme south of the Osa Peninsula. The deformation is quite big here. It's reached 5 centimeters in D7 and 1.5 centimeters in D7, so it's quite big. And the particularity was that even if this point move a lot, the other ones move also in the same direction. We cannot see really the vector because this one is so big, but they are also move in the direction, but a lot less, which which points to a really shallow slow slip event. So here you have the trench, more or less. We found that the slip were around 3 centimeters, but really shallow to create this pattern of deformation. And just after that, so it was in April, end of March, April, and just after that, an earthquake, small earthquake, a magnitude 6, I think, and after another slow slip, or well, co-seismic, post-seismic, but I prefer to say like a slow slip event just after. We saw many signals there because, well, yeah, the interface is not well defined, and I think there a lot of stuff was going down with a lot of water. The last event I'm gonna talk about is a really interesting event. We were working with Marino and Esteban on that. This is there were 2 events in 2019 in about a month, separated by just a month. 2 strike stick events, one here, the first one, and we didn't know which side. Well, it was hard to know exactly, but we recorded with GPS also. So and just after, a month after, we have another one, magnitude 6, just a few kilometers in the south, and we could model the first one quite well using the deformation of the GPS, and it was intraplate of Caribbean, so between 10 and 20 kilometers, and right lateral slip. You see here, this is the A prime, so A prime, the model, this modeling. So it was quite interesting because the next one was at 30 kilometers, so it's way deeper. And if you remember the tectonic context, one was here, but intra-Caribbean plate, even if the strike slip was supposed to be between Coco and Nazca plate. And the next one, 30 kilometers between like Nazca, Coco plate. I don't know exactly where is the limit there, down there. But, well, quite interesting. We have the data, we can model it, and but we still have some, well, a lot of questions about it. But yeah. So yeah, I come to the end of my presentation. I just want to say that, well, this system, the SOGEOD, is also shared with other institutions like INGEMET in Peru, thanks to the system, and well, most of all the data. They can infer also like the magma reservoir of Sabancaya in Peru, and we have also the same like kind of well, we share also the script with Colombia. So yeah, that's it. Just maybe about the data. We have a bilateral open access policy, so it means, yeah, we want to share the data with other institutions, sorry, but like in a way that, yeah, both scientists can gain in this collaboration. And we also share our software and script. That's it. So thank you very much.